Science fiction, a world where we can step outside reality in order to look at the implications of technology's achievements, where we can speculate about what the future holds for society. Science fiction first appeared at the dawn of the Industrial Revolution. As engineers designed and built machines to save people's labor, science fiction writers took an interest. Some were uncomfortable with the enormous potential of machines to affect society. What assurances were there that these machines would stay under our control and would not harm us or even replace us? And what better engineering innovation to use to raise these issues than robots, machines with minds of their own? As a result of the fears expressed in stories and films of the early 20th century, engineers did their design of robotics applications against a backdrop of suspicion. This segment from the comic book series Magnus Robot Fighter 4000 AD, published in the mid-60s, demonstrates the high level of mistrust of robot capabilities.
That does it.
Are you all right?
Yes, but in another second, it would have been a different story.
The reality of contemporary industrial robotic engineering has been very different. Robots have brought about more productive manufacturing lines and greater quality assurance. Their use has saved people from having to work in hot, toxic, or otherwise dangerous environments. Automated production lines using robots are chalking up an admirable safety record. However, industrial robots have injured people, and injuries may occur more frequently as the number of working robots increases. In at least one case in 1984, a worker was killed. The victim entered the working range of the robot, presumably to clean up scrap metal that had accumulated on the floor. The work cell control systems did not sense his presence, and as a result, the worker was pinned between the back end of the robot and a steel safety pole. His heart stopped. No matter how automated a manufacturing line is, there are sure to be workers around who must be protected. Line operators. Maintenance workers, programmers, managers, and visitors. Robots have weak sensing capabilities, so they can't be relied upon to always react in a safe way when these workers approach. Safeguarding robots is more complex than safeguarding other types of machines. Their range of movement is much greater than other machines. Machine guards around belts, other moving parts, and points of operation are small in comparison to robotic work cells that often encompass several cubic yards on the plant floor. Robot guarding has to be flexible, too, to adapt to the variety of tasks a single robot may perform. Industrial robots are hardly on the attack, but they can be a hazard, and engineers are clearly the people who must take responsibility for ensuring the safety of the people who work with them. The next few minutes will highlight some of the ways to protect people in robotics environments at critical stages of the engineering job: research, design, and implementation. It is extremely important to know as much as possible about the robot before workstation design begins. You have to know the precise track of its movement and how those moves are programmed. Since safe design solutions often involve barriers, it is important to know the range of velocities, payload limits, and tooling options that are required for the job. The barriers must not only keep people out of the work cell, but also keep the machinery within. You must know the features for robot control that the robot manufacturer provides. Alterations to the input-output system are the primary means of designing a safe application. You probably know that robots have emergency stop buttons to provide total shutdown and interruption features to stop arm motion. Interruption circuitry in a robot should be supplemented by hardware stops that will stop the arm even at its full payload and speed. Almost all robots have these stops. They're usually set at the maximum range of the robot. Engineers should have these reset to the limits of movement for the task at hand. And don't ever substitute a steel pole on the shop floor for one of these stops. When workstation design starts, use what you have learned in the research phase. Omitting pinching points is a major consideration. All of the machinery that will be used on the line must be planned for and spaced to allow humans to safely pass. Use templates or models to do this if necessary, no matter what form they take. Obstacles of all kinds must generally be removed from the robot cell. Plan space for end effectors too. A change in tooling can significantly increase the size of the work cell. After determining size and spatial relationship of the equipment, design the isolation of the work cell. There are several different kinds of perimeter guards. Each has its strengths and weaknesses. Barriers that are easy to pass through or over are by themselves inadequate. Fencing is effective and inexpensive. It should be tall enough to discourage workers from climbing. Access gates should be interlocked with the robot controller to interrupt the robot cycle if opened. Resetting should require a two-step process. One reset at the site of the interruption and one outside the barrier. A drawback to fencing is that it is difficult to move. Another is that it obstructs the vision of workers who may need to monitor the robot cell. Safety glass or other transparent barriers cost more than fencing, but they solve the vision obstruction problem. Light curtains are another form of useful barrier system. They are available in many sizes, and they can be selectively blanked to provide access to the cell for specific pieces of equipment or products, while still sensing and interrupting the robot cycle for humans. Unfortunately, other things in the environment besides workers may trip a light curtain circuit. Make sure that your operation is clean enough to use them. Pressure-sensitive mats are another effective barrier. Their drawbacks are the possibility of unintended interruption of the robot cycle and the amount of floor space they take up, since they have to be greater than a step wide. If at all possible, locate the operator control panel for the work cell outside the barrier. Both emergency stop and hold or interrupt controls should be on the panel. A second control should be on the panel that must be activated before automatic cycling can be restarted. Several other emergency stop buttons should be located in places of easy access around the work cell. The key to successful use of these barrier devices in your design is redundancy. At this facility, all the cells are guarded by interlocked doors that automatically interrupt the robot when their microswitches are tripped. Warning lights are used to alert workers to problem situations. The operator control panel allows total control of the cell from outside. There is a total line shutdown pull cord system that has a cord drop over each workstation. Each one will shut down the entire line. Although safe manufacturing systems can be engineered with today's technology, there will be increased pressure for more innovation.
Unfortunately, the fencing that you set up provides you with a narrowing of your real estate on the factory floor. Likewise, it makes it a little bit difficult for somebody to go in and do teaching of a robot of a new task or preventative maintenance on a robot, because you have these hard stops. We have sensors that are capable of detecting the human's motion within that environment and tracking the human to be able to differentiate the human movements from the machine movements within its workspace. And what we did was integrated these 4 sensors into a system, a prototype safety system, in which we were able to detect human movement based upon, in the capacitive world, a change in the dielectric constant that's associated when a human moves in on the capacitive sensor versus the capacitive sensor moving in plain air. The infrared sensing based upon the change in temperature when a human moves into the environment. The ultrasonic would change the distance that objects appear from the robot end effector, if you will. And the microwave looked at any motion that was present in the environment that was not supposed to be there. And it's important to understand that the variety of applications that we have in different automated workspaces today mandate different sensory implementations as well. Ultimately, what you're trying to do is build the safety system to a same level of intelligence that the actual workplace requires.
After you have designed your robotic work cells, you must install them and get them running. You will probably rely on other parts of your organization to help get the job done. Documentation of your design is important to the purchasing department and to the facilities people who actually put the system together. Complete documentation details the results of your planning. It ensures that the robots are adapted to your own requirements, including the cell barrier systems. The robot manufacturer can look at your documentation as a check on the match of his product with your needs. Documentation also provides a way to record the inevitable changes in your design that will be made during installation and debugging. Remember to check those changes for their impact on the safety of the system. There are a number of systems safety techniques that can be used to analyze virtually any type of manufacturing system for hazards. They are useful in the design stages as well. During the installation, have the maximum work envelope of the robot marked on the floor as an added visual warning. Make sure the markings are made on the basis of the largest end effector that will be in use. Well-engineered production systems must have well-informed and motivated worker populations to be successful. Preparing the workforce to program, maintain, and operate a robotics production line takes just as much planning as the production line itself does. Training should occur as close as possible to the startup of operations. Everyone on the shop floor will need to learn the basics of robot operations and the emergency shutdown procedures. Startup, maintenance, and programming procedures will be learned by fewer employees, but they must be taught and tested before installation is complete. Refresher courses will be necessary for everyone. When maintenance of longer duration is performed, lockout and tagout procedures should be implemented to make sure that the robot or associated equipment is not re-energized before the maintenance activity is completed. The points of control should be locked out so that re-energizing the robotic system can only be done by the person who applied the lockout. A warning or tagout should also be posted at the point of control. It should provide information as to why and by whom the energy sources were isolated. To review, research before you begin design of robotic applications. You must know the capabilities and the control mechanisms of the robots in detail. Design your system to do the work without peril to workers. Use redundant barrier and control systems, the ones best suited for your operation. Install your production line with the same care you used during design. Fully document any changes in the design. Make sure that everyone is trained on all aspects of the new production line. 20 years have passed since robot fighter Magnus was created. Science fiction writers of the 80s still see potential dangers of robotics. But now, robots are often used to represent good in stories. Films, books, and toys present benevolent robotic characters. Clearly, there has been a shift in public perception of the dangers, brought about partly by good, safety-conscious engineering. The quality of today's engineering designs for industrial robotics applications will shape the views of the public, the workforce, and today's science fiction writers, and help determine whether scenes like these will ever be part of robot reality.